Welcome to Cosmic Sedation, where stars gently guide you into peaceful slumber. Tonight, we drift toward the edge of tomorrow, exploring cosmic expansion at the galactic arm's frontier in 5 billion years. Subscribe and like if you're as curious about the cosmos as I am. Where are you listening from tonight? And what time do you usually fall asleep? Let's dive into this tranquil journey together. In 5 billion years, our galactic arm will stretch to a radius of 200,000 light years from its current 50,000, expanding not by growth within, but by an invisible force pushing it apart: dark energy. The edges of this future spiral are moving outward at astonishing speeds. Here, the Milky Way's periphery is creeping away from the galactic center at about 30 kilometers every million years. This subtle drift might seem insignificant, yet over time it accumulates to a staggering velocity that will soon exceed 90% of light speed. For reference, if this expansion rate were applied to Earth's distance from the Sun today, we would find ourselves traveling away from our star by more than 10 times the distance between here and Mars in just 1 year. The paradox lies in the fact that while galaxies drift apart, they become increasingly isolated, unable to communicate through signals or light. Dark energy is an enigmatic force that now dominates the cosmos, accelerating the expansion of space itself. This unseen pressure operates on scales far beyond our comprehension, acting not like gravity, but as its opposite, pushing rather than pulling. The temperature at the edge of this expanding galactic arm will plummet to less than 5 degrees above absolute zero, a chilling minus 268 degrees Celsius. Such cold would freeze even the most volatile molecules into rigid structures, stifling any possibility for new stars to form. In contrast, consider Earth's coldest recorded temperature, nearly minus 90 degrees Celsius in Antarctica. This environment is over 3 times colder, making it impossible for anything as we know it to exist. At this future boundary of our galactic arm, the cosmic microwave background radiation will have cooled to a mere 0.5 Kelvin, just fractions above absolute zero. This faint glow, a remnant from the Big Bang, will no longer be detectable in visible light, but will instead shift into radio frequencies, becoming a relic of the universe's infancy. The stars beyond our local group are already moving so rapidly away that their light is stretched to wavelengths we cannot see, rendering them invisible to us. This cosmic isolation means that for any hypothetical observer at this distant edge, they would find themselves in an increasingly dark and silent void. As the galactic arm expands, it also rotates, a complex interplay of forces shaping its evolution. The Sun will have expanded into a red giant with a radius up to 1 astronomical unit, effectively encompassing Earth's current orbit around it. This expansion marks the end of our solar system as we know it. Mercury and Venus would be swallowed by this bloated star, while Mars and beyond might find themselves in new orbits or even ejected entirely from the stellar embrace. The iron in your blood was forged in stars that died long before our sun formed. Yet now, these ancient elements will witness a transformation of their host galaxy into an increasingly isolated outpost within the vastness of space. 5 billion years hence, the edge of the Milky Way's galactic arm will be 35,000 light-years farther from its current position. This expansion is not only due to dark energy, but also influenced by the eventual merger with Andromeda, forming a new elliptical galaxy called Milkomeda. As this process unfolds, stars at the periphery are slowly becoming more isolated in their vast, empty surroundings. New star formation will slow dramatically as molecular clouds disperse or become too sparse for gravity to pull them together effectively. The universe is on its way to a future where galaxies drift apart into cosmic loneliness, each one encased in an ever-growing bubble of isolation. At 5 billion years from now, the edge of our galactic arm will have expanded to a radius of 35,000 light-years further from its current position. Yet this expansion is not merely spatial. It marks an extraordinary journey across distances so vast they challenge human comprehension. Imagine standing at the edge of the Milky Way's spiral arm. The temperature here hovers around -268 degrees Celsius, colder than any naturally occurring place on Earth. This frigid environment inhibits star formation due to sparse molecular clouds. Yet it is in these very regions that dark energy exerts its relentless influence. Each hydrogen atom drifting through this space moves apart from every other at increasing velocities, a cosmic dance orchestrated by forces we can barely fathom. Consider the scale. A single human cell contains approximately 10 trillion atoms, each smaller than a billionth of a meter. Yet in contrast, the distance between stars here is on average 40,000 light-years, a span so immense it would take over 100 billion years for light to traverse if we were to lay down one atom after another without interruption. This vastness underscores our microscopic insignificance within cosmic structures. Remarkably, this same principle of increasing separation applies not just locally, but also across the observable universe, where galaxies are moving away from each other faster than the speed of light due to dark energy's accelerating effect. The Sun will have swollen into a red giant by this time, its outer layers extending up to the Earth's current orbit. Were a human present here, they would experience the Sun's immense gravitational pull as it distorts nearby space-time. The red giant phase marks the end of our star's life cycle, yet other stars are already extinguishing at the edges of observable galaxies. Redshifts push their light far beyond visible spectrums. In this environment, a human observer would find themselves in a place where stars appear distant and sparse, an isolated outpost in a universe expanding beyond our ability to comprehend or explore directly. At this point in galactic history, the cosmic microwave background radiation has cooled to just half a Kelvin, an ambient glow left over from the Big Bang. This faint echo contrasts sharply with the dynamic processes shaping our local environment. The Sun's expansion, the merger with Andromeda forming Milkomeda, and the accelerating separation of distant galaxies due to dark energy. Our galaxy will become part of this elliptical structure, yet it remains an island in a universe where most light has redshifted out of reach. The temperature at the edge of our galactic arm is so low that molecular hydrogen struggles to form, a critical ingredient for new star birth. This scarcity underscores how conditions conducive to life are increasingly rare as we move outward from the galactic core. In this environment, a human observer would find themselves in an area where stars appear distant and sparse, a lonely outpost in a universe expanding beyond our ability to comprehend or explore directly. Moreover, the cold temperatures here could freeze even the most resilient biological systems, highlighting how inhospitable such regions are for life as we know it. The vast distances between celestial bodies challenge scientific exploration and philosophical understanding, pushing us to reconsider our place in this evolving cosmos. In 5 billion years, the Milky Way will merge with Andromeda, forming a new galaxy called Milkomeda. This merger will drastically alter the local environment, but it won't significantly affect regions at the edge of the galactic arm, where the expansion continues unchecked. The merged galaxies will consist of billions of stars orbiting in an elliptical pattern, while distant galaxies continue their accelerated retreat into the depths of space. As dark energy dominates the universe's expansion rate, these far-off galaxies will eventually disappear from our view, leaving us with a smaller observable universe and a more isolated galaxy cluster at its core. The cosmic microwave background radiation, now cooled to 0.5 Kelvin, provides a snapshot of the early universe when it was about 380,000 years old. This temperature is nearly absolute zero, yet in this environment, it serves as a reminder of the hot, dense state that once dominated the cosmos. The contrast between this frigid backdrop and the energetic processes ongoing within our galaxy highlights the dynamic nature of cosmic evolution. For a human observer, the coldness here would be unbearable, with temperatures so low they could freeze even the most resilient biological systems. This environment is not just isolated, it's inhospitable, underscoring how life, as we know it, thrives only in specific niches within the vast cosmos. Interestingly, despite these harsh conditions, some scientists speculate that certain extremophiles might survive in such extreme environments, challenging our understanding of what constitutes habitable zones. 5 billion years from now, an astronaut floating near the edge of our expanded galactic arm would find themselves in a space where stars are few and far between. The interstellar medium is so sparse that it's akin to drifting through the emptiest desert on Earth, yet with no wind to disturb you. Here, even the faintest glow from distant stars provides minimal warmth, and each atom encountered becomes a rare event. The density of this region has dropped to about 1 atom per cubic centimeter, making each collision with an atom an exceedingly rare occurrence. In such an environment, a gentle push by these atoms would take decades for the astronaut to notice any change in their trajectory. This emptiness is profound not just because it's vast, but also because it marks the beginning of the universe's isolation, each galaxy moving further from its neighbors at velocities approaching light speed. At this distance, cosmic microwave background radiation has cooled to a mere 0.5 Kelvin, barely above absolute zero. The coldness is so deep that it challenges our understanding of temperature itself. For an astronaut floating here, The sensation would be akin to being in a freezer colder than anything we've ever experienced on Earth, yet without the familiar solidity or noise of mechanical refrigeration. This region's extreme coldness also affects molecular formation, making star birth rates significantly lower. The rate of expansion continues to accelerate due to dark energy's influence, causing distant galaxies to appear dimmer and redder with each passing moment. Closer stars still emit visible light, though they are fewer in number. The astronaut would feel an eerie isolation as the universe stretches around them, with only a few nearby stellar companions for company. This loneliness is compounded by the knowledge that the expansion will soon render even these neighbors too distant to observe. At this edge of space, molecular clouds have dispersed or thinned out so much that new stars cannot form in any significant numbers. The coldness and sparsity here are not just a result of cosmic expansion, but also signal the end of an epoch where galaxies birthed stars at their peak rates. An astronaut might notice how the light from nearby stars flickers less frequently than it does today. Each star is now further apart, making the universe feel more like a scattered collection of islands floating in the void. The temperature near this point is so close to absolute zero that atoms barely move. In fact, some areas are so cold they approach temperatures found only in specialized laboratories on Earth designed for quantum experiments. This contrast between the natural coldness of space and human-made environments highlights how we have learned to manipulate our surroundings far more than nature has ever intended. For an astronaut floating here, this realization would be a quiet reflection upon the limits of both exploration and creation. The interstellar medium at this edge is so thin that it offers little resistance against cosmic rays or high-energy particles from distant stars. An astronaut's suit must provide constant protection, as even brief exposure could cause radiation damage. This environment underscores the fragility of life in such extreme conditions, where survival depends on advanced technology rather than natural shelter. As they drift through this sparse vacuum, they might reflect on how our bodies are a mere speck compared to the vastness around them. The expansion of space itself is relentless here, and over time, even the nearest stars will become dimmer as they recede further into the distance. This gradual dimming would be subtle but unmistakable, a slow fading of light sources that once seemed eternal. The astronaut's journey through this region serves as a poignant reminder of both our place in the cosmos and the inevitable passage of time. Each star they pass is not just a distant beacon, but also a witness to epochs past, their light carrying messages from billions of years ago. The coldness at the edge of the galactic arm affects more than just molecular formation. It impacts the behavior of atoms themselves. At such low temperatures, atoms move so slowly that they can be trapped in complex quantum states for extended periods. This phenomenon is known as Bose-Einstein condensation and occurs naturally here under conditions unattainable on Earth without sophisticated equipment. For an astronaut drifting through this region, observing these quantum effects would be a rare opportunity to witness physics at its most fundamental level. As the astronaut floats through this sparse interstellar medium, they might notice that their position in space is constantly shifting due to the gravitational pull of nearby stars and the expansion of the universe itself. This subtle motion means that even though they are drifting slowly, they are never truly stationary. The movement is imperceptible but constant, a reminder that even in the emptiest reaches of space, there is always something happening. Each tiny shift underscores how our understanding of stillness is relative and deeply connected to our perception of time. For instance, the astronaut might observe that their trajectory occasionally aligns with the path of an interstellar dust particle, creating a brief but unexpected encounter that highlights the unpredictable nature of motion in such vast emptiness. In 5 billion years, the edge of the galactic arm will have expanded to a radius of 35,000 light-years further from its current position. Yet this expansion is not merely spatial. It marks an extraordinary journey across distances so vast they challenge human comprehension. The rate at which space itself stretches means that distant galaxies are moving away faster than any conceivable spacecraft could ever travel. This relentless expansion highlights the paradoxical nature of our universe. While we strive to explore and understand, the very fabric of space is pulling everything apart. For an astronaut drifting through this region, it serves as a humbling reminder of both the vastness of the cosmos and the limitations imposed by physics. Specifically, the rate of expansion is such that galaxies beyond a certain distance are moving away at speeds greater than 90% of the speed of light, making them unreachable even for signals traveling at light speed. In 5 billion years, the edge of our galactic arm will extend to a distance of 35,000 light-years from its current position. Here, stars are nearing the end of their life cycles, and one such star is entering the final phases of stellar evolution. This aging star's outer layers begin to unravel, revealing the complex processes within as atomic nuclei break down into simpler elements. Each atom releases energy in a series of decays that ultimately scatter its matter across space. This process forms intricate patterns known as planetary nebulae, which glow faintly with the light from the newly exposed white dwarf at the star's center. Remarkably, this star is not alone. Throughout the universe, similar stars are undergoing their final transformations. In our galaxy, approximately 20 to 30 stars will reach this stage every year. The materials released by these dying stars enrich the interstellar medium, contributing to the formation of new elements and ultimately new stars. For instance, the calcium in your bones was once forged within a star that has since expired. The temperature at this cosmic edge is extraordinarily low, dropping below -268 degrees Celsius. Despite this extreme cold, molecular clouds are still forming and beginning to collapse under gravity, setting the stage for new generations of stars. These nascent stellar nurseries are crucial for understanding how star formation will continue in the expanding universe. Each fragment from a dying star carries not just the elements that make up planets, but also the light echoes of its past. Some of this scattered material may eventually find its way into newly forming solar systems, contributing to the birth of future worlds. The distances between these nebulae are vast. It takes millennia for their light to reach us, and some will never be seen as they are redshifted out of our observable universe. Meanwhile, the white dwarfs at the centers of these planetary nebulas slowly cool down over billions of years, eventually becoming dark objects known as black dwarfs. These remnants continue to influence their surroundings by exerting a gravitational pull on nearby clouds and contributing to the overall structure of galaxies. The cycle continues, with past stellar generations shaping future star formation regions. The interstellar medium near these dying stars is incredibly tenuous. It contains fewer than 10 particles per cubic centimeter, compared to over 1 million at Earth's surface. Yet within this sparse environment, the remnants of stellar death play a vital role in sculpting future star formation regions. The diffuse gas clouds that surround these nebulae are slowly accumulating material from their surroundings, gradually growing into dense enough structures for new stars to begin forming. Each planetary nebula is unique, shaped by the specific characteristics of its parent star. Some are symmetrical and circular, while others take on more complex shapes like hourglasses or even butterfly wings. These intricate patterns are a result of how the stellar wind from the dying star interacts with surrounding material and magnetic fields. As we observe these distant nebulae, it's important to remember that they represent not just the death of stars, but also their rebirth in another form. The elements scattered by these cosmic events will one day contribute to the formation of new solar systems and planets, carrying forward the legacy of past stellar generations into the future. The rate at which galaxies move away from each other is increasing due to dark energies' accelerating effect on cosmic expansion. In 5 billion years, distant galaxies will appear increasingly faint and redshifted out of our visible spectrum. The Milky Way's merger with Andromeda will create a new elliptical galaxy called Milkomeda, further altering the landscape of our local universe. Even at -268 degrees Celsius, certain processes can still occur within the interstellar medium near these dying stars. Molecular hydrogen can form under specific conditions, providing raw material for future star formation, despite the cold temperatures and sparse environment. This shows how resilient cosmic processes are, capable of continuing even in the harshest environments. The expansion of space causes distant galaxies to move away from us faster than the speed of light, meaning their light will never reach us. Yet within our galactic arm, the remnants left behind by these dying stars continue to influence star formation and sculpt future stellar generations. Im Start, Limburg. In 5 billion years, the universe will be a place where expansion is more pronounced than ever before. Distant galaxies, now mere specks of light in our telescopes, will have moved so far away that their light no longer reaches us within the visible spectrum. This accelerated expansion will reshape the cosmos, making even familiar celestial landmarks seem distant and alien. The edge of the Milky Way's spiral arms is set to expand outward by about 35,000 light-years from its current position. To put this into perspective, consider that if you were standing at one end of our galactic arm today, it would take light more than 100,000 years to reach the other end. In 5 billion years, this distance will have nearly doubled, a journey that now takes twice as long for photons to traverse. This vast increase in size is not just about space stretching, but also signals a universe growing colder and emptier. The temperature at the edge of our galactic arm will plummet below 4.5 Kelvin, making it one of the coldest regions known in the cosmos. At this temperature, molecular clouds, which are essential for star formation, become unstable and disperse. This cooling trend is part of a broader pattern. As the universe expands, its overall energy density decreases, leading to conditions that are less favorable for new stellar birth. The irony here lies in how expansion, while creating more space for galaxies to exist, paradoxically makes it harder for new stars to form. The rate at which distant galaxies move away from each other will exceed 90% of the speed of light by this time. This acceleration is driven by dark energy, an enigmatic force that permeates all of space and accounts for nearly 3/4 of the universe's total mass energy content. In contrast to the slower expansion observed today, in 5 billion years, distant galaxies will be so far apart and moving at such velocities that they might as well inhabit entirely separate universes. So vast is their separation. Our ability to observe these galaxies directly will diminish because their light shifts into wavelengths beyond our telescope's reach. The merging of the Milky Way and Andromeda, forming Milkomeda, will mark a significant change in local cosmic structure. This galactic collision is expected to occur around 4 billion years from now, with the final consolidation taking place approximately 1 billion years later. The resulting elliptical galaxy will be more than twice as massive as either of its progenitors and could host up to 10 times as many stars. Despite this merger, which involves the most complex gravitational interactions on a cosmic scale, the overall trend in the universe is toward greater isolation, a paradox where local density increases while global connectedness diminishes. The cosmic microwave background radiation left over from the Big Bang will have cooled to about 0.5 Kelvin by then. This cooling process reflects the gradual dilution of energy across an ever-expanding universe. At this temperature, any remaining particles in space will be moving at speeds so slow they could almost freeze in place, effectively becoming immobile on human timescales. While this radiation no longer serves as a reliable indicator for cosmological studies due to its extreme redshift, it continues to trace the ancient history of our universe, offering clues about its earliest moments and the conditions that shaped its expansion. In 5 billion years, regions will exist where space expands faster than light speed, creating a horizon that can never be crossed. This boundary marks an area beyond which no information or signal from distant galaxies could reach us due to the accelerating expansion of the universe. The edge of our galactic arm will have expanded to a radius of 35,000 light-years further from its current position, marking a significant journey across distances so vast they challenge human comprehension. At this horizon, cosmic microwave background radiation has cooled to about zero point 0.5 Kelvin, making it the coldest place in our observable universe. This temperature is colder than any laboratory on Earth, where scientists strive to achieve such low temperatures for experiments. Yet, at this extreme cold, molecular formation becomes nearly impossible, affecting star birth rates and the distribution of elements essential for life. By 5 billion years from now, dark energy will dominate the expansion rate of the universe, causing galaxies beyond our local group to move away faster than light can travel. This phenomenon means that while we might observe these distant galaxies today, their future light will never reach us within the visible spectrum due to cosmic acceleration. The paradox here is that although we see them now, they are already unreachable in terms of communication or exploration. For instance, a galaxy currently at 10 billion light-years away could be moving so fast that its light, which has been traveling for billions of years, will never reach us as it stretches beyond our observable universe. The temperature at the edge of our galactic arm will drop below -268 degrees Celsius, affecting molecular formation and star birth rates. In such extreme cold, even basic chemical reactions slow down significantly. This environment is inhospitable for new stars to form, as the necessary molecular clouds have dispersed or are too sparse to sustain the required reactions. Interestingly, this cooling process also affects black holes, causing their event horizons to shrink slightly due to the reduced energy density in space. In 5 billion years, our galaxy will merge with Andromeda, forming a new elliptical galaxy known as Milkomeda. The two galaxies are expected to collide at an estimated speed of 400 kilometers per second, creating shock waves that will trigger star formation and supernovae across both systems. This merger process will take several billion years to complete, during which time the Milky Way's spiral arms will have expanded to a radius of approximately 200,000 light-years from their current 50,000, expanding not by growth within, but by an invisible force pushing it apart: dark energy. At this time, interstellar travel between distant galaxies cannot be achieved because the distances and speeds involved far exceed any feasible propulsion technology. The universe's expansion rate is expected to increase, causing galaxies at extreme distances to move away from us at velocities exceeding 90% of the speed of light. This acceleration underscores the transient nature of our cosmic neighborhood and highlights how quickly distant regions become unreachable. In this environment, sound cannot propagate because there are no molecules to carry pressure waves, leaving an absolute silence that contrasts sharply with the bustling activity closer to the galactic core, where stars and planets continue their dance. Beyond this horizon, galaxies will not only be moving away from us at velocities exceeding 90% of the speed of light, but will also appear increasingly redshifted out of our observable spectrum. This phenomenon is known as cosmic redshift, where the wavelength of light stretches due to the expansion of space itself. As a result, what once appeared as vibrant stars and galaxies now dim into invisibility, their light stretching beyond the limits of human perception. In this future environment, even if advanced civilizations were to exist in these distant regions, communication would be impossible. The vastness of space at such scales becomes not just a physical barrier, but also a temporal one. Events that occur in these far-off galaxies will unfold long after our universe has forgotten their existence. This paradoxical scenario underscores the transient nature of our cosmic neighborhood and highlights how quickly distant regions become unreachable, emphasizing the profound isolation of each galaxy within this expanding cosmos. The universe's expansion rate is expected to continue increasing, pushing these distant realms further into an unobservable darkness, a fate that serves as both a reminder of our own insignificance in the grand scheme of things and a testament to the relentless march of time across the vast expanse of space. In 5 billion years, the Milky Way and Andromeda will have merged into a new galaxy called Milkomeda. Their combined mass creates gravitational waves that ripple far beyond their visible boundaries, influencing molecular cloud formation and young star birth rates within them. The merging process is not instantaneous. It takes time for each galaxy's structure to intertwine, shaping the spiral arms we observe today. This slow dance between galaxies has been occurring for billions of years, sculpting the intricate patterns we see across the cosmos. Dark matter's gravitational pull shapes galaxy structures, though it remains invisible to direct observation. In 5 billion years, this unseen force will have sculpted Milkomeda into an elliptical form where spiral arms are no longer discernible. The formation of these arms is a delicate balance between the inward pull of gravity and the outward push of rotational forces. This dynamic tension creates the beautiful patterns we observe in current galaxies, like our own Milky Way. Yet, as Milkomeda takes shape, this delicate balance will shift, leading to an overall smoother structure without distinct spiral features. At the edge of what was once a galactic arm, the temperature hovers just above absolute zero at -268 degrees Celsius. Here, interstellar space is nearly empty, with particles so sparse that they rarely collide. In contrast, Earth's atmosphere at sea level contains approximately 100 trillion times more gas molecules per cubic centimeter than this region of space. The absence of molecular collisions means that sound cannot propagate here. Instead, any acoustic disturbance would dissipate almost instantly due to the vast distances between particles. This profound stillness stands in stark contrast to the bustling activity within denser regions of galaxies, where stars are born and die. The formation of galactic arms requires specific conditions: a sufficient amount of gas and dust, rotational forces, and gravitational interactions with other galaxies. These factors come together over billions of years to create the familiar spiral patterns seen in many galaxies today. In 5 billion years, as Milkomeda settles into its final form, an elliptical galaxy with an average diameter of 200,000 light-years, the arms will have faded away due to the dispersal of interstellar material. The process by which they formed is a complex interaction between cosmic forces, gravity pulling inward and rotation pushing outward. This delicate equilibrium allowed for the birth of stars within those arms, contributing to the rich diversity of stellar life that exists today. However, an unexpected factor in this formation is magnetic fields, which can twist and shape gas clouds, sometimes creating more intricate patterns than gravitational forces alone. In 5 billion years, the edge of what was once a galactic arm will be 35,000 light-years further from its current position due to both expansion and rotation. This vast distance is equivalent to traveling across nearly 200,000 times Earth's diameter, a scale that challenges our ability to comprehend such expansiveness. The journey to this point would take thousands of years, even if traveling at the speed of light. Yet, despite the immense distances involved, it's a testament to the interconnectedness of cosmic forces, gravity, rotation, and expansion that shape galaxies over eons. The temperature at the edge of the galactic arm is expected to drop below -268 degrees Celsius, affecting molecular formation and star birth rates. This extreme coldness has profound implications for the future of star formation in these regions. The cooling process begins with the expansion of space itself, which stretches light waves and reduces their energy. As a result, even the faintest heat from distant stars becomes undetectable against the backdrop of this cosmic chill. In contrast, Earth's atmosphere at sea level contains approximately 100 trillion times more gas molecules per cubic centimeter than this region of space. This vast difference in particle density means that sound cannot propagate here. Instead, any acoustic disturbance would dissipate almost instantly due to the vast distances between particles. The silence is absolute and unbroken by any form of acoustic disturbance. In 5 billion years, sensors at the edge of our galactic arm will detect subtle ripples in space-time gravitational waves from distant black holes colliding. These instruments are finely tuned to measure minute distortions that stretch and compress space by fractions of an atom's width. Each ripple carries information about cataclysmic events billions of years old, yet the effects here are so slight they would be imperceptible without advanced technology. These detectors act like microscopes for space-time, revealing secrets hidden in the cosmic fabric. These instruments can detect changes smaller than a proton's diameter, disturbances that would otherwise go unnoticed. They record events of immense scale, black holes merging, each containing billions or even trillions of times more mass than our Sun. These collisions generate gravitational waves that travel through space at the speed of light, undisturbed by cosmic expansion. The detectors are like sentinels, capturing these faint signals from across vast distances, providing insights into the universe's most violent transformations. While these ripples traverse billions of light years, they maintain their integrity due to the nature of space-time itself. Space stretches and contracts with them, ensuring that every point along their journey is influenced equally by the event's energy. This consistency allows scientists to trace back the exact moment and location of a collision, even though the light from these events has long since been redshifted out of our visible spectrum. In this environment, where stars are few and far between, gravitational waves become one of the most reliable means of understanding distant phenomena. At the edge of our galactic arm, temperatures hover just above absolute zero, around 4.5 Kelvin. This cold environment is almost a laboratory for quantum effects, where molecules struggle to form and stars have long since ceased to shine brightly. The coldness here contrasts sharply with the heat and light of the galaxy's core. Yet it is in these regions that the universe's most profound mysteries are revealed through gravitational waves. These waves travel unimpeded by the sparse molecular clouds that dominate this region, making them an invaluable source of information about the cosmos' deepest reaches. As we consider these subtle ripples in space, it's worth noting their paradoxical nature. They are both incredibly minute and yet carry immeasurable information across cosmic scales. A single detection can reveal details about black hole mergers from galaxies far removed, events that would otherwise remain hidden from direct observation due to the vastness of space and time. The detectors at this edge of the galactic arm are not merely passive receivers, but active participants in a grand cosmic narrative, one where every signal contributes to our understanding of the universe's evolution. In 5 billion years, as we contemplate these gravitational waves at the edge of the galactic arm, it becomes clear that even in the most remote corners of the cosmos, connections are being made across unimaginable distances. These ripples carry stories of stellar collisions and the eventual fate of galaxies themselves. They remind us not only of the vastness of space, but also of its intricate web of interlinked phenomena. 5 billion years from now, the edge of our galactic arm will have expanded by 35,000 light-years from its current position. This expansion is not just a static increase in size, but an active reshaping of the galactic structure. The Milky Way and Andromeda, having merged into Milkomeda, will exert a stronger gravitational pull on nearby galaxies like the Triangulum Galaxy. As these galaxies drift apart, their relative positions shift, altering the dynamics of their interactions. At this expanded edge, temperatures hover around 4.5 Kelvin, just above absolute zero. This extreme cold affects molecular formation and star birth rates. It is not the vast distance from stars that causes such low temperatures, but rather the cooling effect of cosmic expansion, stretching out the radiation left over from the Big Bang. In contrast, a laboratory on Earth can achieve even lower temperatures through advanced refrigeration techniques. The temperature at this point is so cold that it challenges our understanding of how molecular clouds form and maintain their structure. The rate of cosmic expansion accelerates to the point where distant galaxies move away at velocities exceeding 90% of the speed of light. This acceleration means that within our local group, gravitational interactions become more complex. The Andromeda-Milkomeda collision is a unique event in this expanding universe, where two large galaxies merge amidst an accelerating expansion rate. As they combine, their combined mass creates gravitational waves that ripple far beyond their visible boundaries. The interstellar medium at the edge of the galactic arm is so sparse that it resembles drifting through the emptiest desert on Earth, yet with no wind to disturb you. This vastness contrasts sharply with the dense molecular clouds found closer to the galactic center, where star formation thrives. The expansion has dispersed these clouds, making new stars increasingly rare at the periphery. In this region, the density of interstellar matter is so low that it would be nearly impossible for a human observer to detect any significant presence without sophisticated instruments. In this future environment, sound cannot propagate because there are no molecules to carry pressure waves. This isolation means that even if you were near a star at the edge of the expanded galactic arm, you would hear nothing but silence. Yet paradoxically, this absence of sound amplifies our understanding of space's vastness and emptiness. The cold temperature, just above absolute zero, further underscores the extreme conditions necessary for molecular clouds to form. Here, the universe is a place where light itself becomes stretched into wavelengths beyond human perception. By 5 billion years from now, the local group structure will have changed dramatically due to cosmic expansion and stellar evolution. Galaxies at the edge of this group will be moving apart so quickly that they appear frozen in place from our perspective. The distance between these galaxies continues to grow at an accelerating pace, making it increasingly unlikely for any new interactions or mergers to occur among them. Each galaxy becomes more isolated in its journey through this expanding universe, a silent testament to the vastness and solitude that cosmic expansion brings. As they drift further apart, their gravitational influence diminishes, affecting not only their future collision probability, but also the potential for new star formation in the intergalactic voids between them. In 5 billion years, the edge of our galactic arm will stretch out to a distance of 35,000 light-years from its current position, marking where cosmic expansion overtakes local gravitational forces. This boundary is not static, but dynamic, constantly shifting as the fabric of space stretches under the influence of dark energy. Here, the universe's expansion accelerates, pulling galaxies apart at velocities exceeding 90% of the speed of light. The interstellar medium becomes increasingly sparse, with a density less than 1 atom per cubic centimeter, creating an environment where sound cannot propagate and molecules struggle to form. At this frontier, temperatures plummet to just 4.5 Kelvin above absolute zero, cold enough for even hydrogen atoms to freeze in place. This cooling process preserves some faint signals from the early universe, offering astronomers glimpses into epochs long past. The cosmic microwave background radiation has cooled to about 0.5 Kelvin, a temperature so low that it challenges our understanding of how matter behaves at such extremes. In this environment, new star formation is nearly impossible due to the scarcity of molecular clouds necessary for stellar ignition. The stars at this boundary are few and far between, creating an environment where light from distant galaxies is redshifted out of visibility due to cosmic expansion. Despite their sparse distribution, these ancient beacons continue to shine faintly, marking the passage of time across billions of years. The interstellar medium here is incredibly thin, with a density less than 1 atom per cubic centimeter, making it nearly a perfect vacuum compared to regions closer to the galactic core. This vast emptiness contrasts sharply with the dense star clusters found near the center of galaxies. By 5 billion years hence, star formation will have slowed dramatically along the edge of our galactic arm due to the thinning molecular clouds necessary for stellar ignition. At -268 degrees Celsius, molecules struggle to form, making it difficult for new stars to ignite in these regions. Yet within this sparse environment, some stars persist, ancient beacons from a time when star formation was more prolific. These remnants of past stellar generations continue to shine faintly, marking the passage of time across billions of years. Despite the extreme cold and lack of molecular clouds, these ancient stars are surprisingly resilient, their cores still fusing hydrogen into helium at rates that defy expectations given the harsh conditions. In 5 billion years, the edge of our galactic arm will merge with Andromeda, forming Milkomeda, an elliptical galaxy that spans approximately 2.5 million light-years in diameter. This cosmic collision will reshape not only the structure, but also the environment of both galaxies, leading to increased star formation near the merging regions where gas clouds collide and coalesce. These collisions will ignite bursts of stellar activity, creating new stars that will live out brief lives before joining the vast dark expanse once more. The gravitational waves from distant black hole mergers will become a significant feature in this region, though these subtle ripples will be too faint to detect without highly sensitive instruments. As we peer into the future from our vantage point today, the edge of our expanding galactic arm will witness a transformation in its cosmic neighborhood. Distant galaxies will recede beyond the observable universe, their light forever lost to us due to the accelerated expansion. Yet within this vast and lonely expanse, remnants of past stellar generations continue to shine faintly, marking the passage of time across billions of years. This cooling process leads to a significant decrease in the number of new stars formed, as the necessary conditions for stellar ignition become increasingly rare. The edge of our galactic arm will also experience an increase in gravitational waves from distant black hole mergers, though these subtle ripples will be too faint to detect without highly sensitive instruments. This phenomenon underscores the intricate dance between cosmic expansion and local dynamics, where forces on vastly different scales interact to shape the universe we know. At the edge of our galactic arm in 5 billion years, the expansion of space will have stretched the cosmic microwave background radiation to a temperature of approximately 0.5 Kelvin. This cooling is due to the relentless expansion of the universe, which stretches out the wavelengths of light and other forms of electromagnetic radiation. The cosmic microwave background, once a bright glow in the early universe, now appears as a faint hum or hiss at microwave frequencies. It carries with it the imprint of the Big Bang, offering insights into the conditions that existed just fractions of a second after the birth of time. The cosmic microwave background's presence here is not merely an echo from the past. It also reflects the current state of cosmic expansion. As dark energy accelerates this expansion, distant galaxies are moving away at velocities exceeding 90% of the speed of light. This rapid expansion stretches the wavelengths of their emitted light, shifting them out of the visible spectrum and into the microwave range. The cosmic microwave background we perceive is a relic from when the universe was much younger and denser, before stars and galaxies began to form in significant numbers. It serves as a cosmic timekeeper, marking the passage of billions of years through its subtle variations. At this distant edge, the temperature has dropped below -268 degrees Celsius, affecting molecular formation and star birth rates. This cooling is due not just to distance, but also to the expansion of space itself, which stretches out the wavelengths of radiation emitted by matter. As a result, atoms and molecules are less likely to collide with enough energy to form new bonds. The cosmic microwave background's presence at this extremely low temperature provides evidence that the universe has been cooling ever since its birth in the Big Bang. This cooling process is not uniform across all parts of space. It reflects the overall expansion rate and the distribution of matter within our observable universe. For instance, regions with higher density concentrations cool more slowly due to gravitational effects, while voids expand faster, leading to a differential cooling pattern. While we cannot hear the cosmic microwave background directly, imagine what a scientific instrument designed to detect these signals would perceive. A faint hum or hiss that contains the history of billions of years, compressed into microwaves. This radiation helps scientists map out the cosmic web, the vast network of galaxies, dark matter, and voids that make up our observable universe. It tells a story of how gravity pulls matter together while expansion pushes it apart, creating structures like clusters of galaxies and superclusters. The cosmic microwave background acts as a bridge between distant epochs in time, connecting us to a period when the universe was uniform and smooth, before cosmic inflation led to the formation of stars and galaxies. For example, scientists have used the cosmic microwave background's anisotropies, tiny temperature fluctuations, to understand how matter clumped together over billions of years, eventually forming the intricate web we observe today. The edge of our galactic arm will have expanded to a distance of 35,000 light-years from its current position. This expansion is not just a static increase in size, but an active reshaping of the galactic structure. As the universe continues to expand, regions beyond our local group are moving so far away that their light no longer reaches us within the visible spectrum. The cosmic microwave background serves as a reminder of this vastness and the limits it imposes on our ability to observe distant galaxies directly. It is a testament to how far light has traveled across an expanding cosmos, stretching and cooling along the way. One unexpected fact is that despite the expansion, some regions of space are actually contracting due to local gravitational influences, creating areas where the fabric of space-time bends inward rather than outward. The cosmic microwave background signal is not only an auditory experience, but also a reminder of our place in the cosmos. It encodes information about the seeds of structure that eventually grew into stars, planets, and life itself. In 5 billion years, as we perceive this faint hum or hiss from the cosmic microwave background, it serves as a link to the origins of everything. Our atoms were forged in ancient stars, long before our sun existed. This radiation is a testament to how far light has traveled across an expanding universe, stretching and cooling along the way. As you listen to this cosmic echo, consider that each particle within your body was once part of the early universe's plasma soup, offering a glimpse into the fundamental processes that shaped the cosmos we inhabit today. At the edge of our galactic arm in 5 billion years, the gravitational field is no longer a static force, but a dynamic entity, influenced by the relentless expansion of space. Stars and gas clouds drift apart as if pulled by an unseen hand, their movements dictated not just by local gravity, but by the cosmic fabric itself stretching between them. This expansion causes distant galaxies to move away at speeds exceeding 90% of light speed, while our local group remains relatively intact, held together by mutual gravitational attraction. Yet, even here, close to home, the stars are subtly affected, like ripples on a pond, their orbits subtly disturbed. The process is akin to observing waves in water, where each crest and trough represents a fluctuation in the density of space-time itself. These fluctuations occur on scales that defy human comprehension, with distances so vast they make our solar system seem infinitesimally small by comparison. For instance, at the edge of this expanding arm, the influence of dark energy stretches space-time to such an extent that it weakens local gravitational bonds between stars and molecular clouds. This weakening leads to a phenomenon known as stellar jitter, where star systems experience irregular movements and shifts in their orbits. Imagine if Earth's orbit around the Sun became less predictable, swinging closer or farther away by unpredictable amounts over thousands of years due to cosmic expansion. Such perturbations might be so slight that they go unnoticed for millennia, yet they accumulate over time, subtly altering the architecture of stellar systems. In 5 billion years, these jitters could become more pronounced, affecting not just individual stars, but entire clusters. The edge of the galactic arm is a region where such effects are most noticeable, as it marks the boundary between stable local structures and the expansive reaches influenced by dark energy. Within this environment, the temperature drops below -268 degrees Celsius, cold enough to freeze molecules solid if they existed in significant quantities. However, the interstellar medium is now so sparse that molecular cloud formation becomes increasingly rare. This cooling and expansion contribute to a less active star-forming region compared to what we see today near the galactic center. The absence of dense gas clouds means fewer opportunities for new stars to ignite, leaving behind older systems with fewer younger neighbors. As cosmic expansion continues to accelerate, it distorts not only space itself, but also time perception in distant regions. In 5 billion years, observers within our local group might notice peculiarities in the orbits of nearby celestial bodies. These distortions arise because space is no longer uniform. Instead, it expands at varying rates depending on proximity to mass concentrations. This non-uniformity means that even though Earth remains relatively stable, the universe beyond appears increasingly chaotic and unpredictable. Interestingly, these gravitational perturbations could lead to unexpected phenomena within stellar systems. For example, binary star systems near the galactic arm's edge might experience altered orbital periods due to the warping of spacetime around them. Such changes would be subtle yet profound, subtly altering the dance of stars that have been moving in harmony for billions of years. This cosmic choreography is influenced not by the familiar pull of nearby masses, but by the distant and unseen influence of dark energy shaping the universe's fabric. The merger of our Milky Way with Andromeda will reshape the cosmic neighborhood we now call home. By 5 billion years from now, these two galaxies will have merged into a single entity known as Milkomeda. This process involves the gentle dance of stars and clouds of gas over billions of years, creating new patterns in the structure of this future galaxy. The outer reaches of the former galactic arms will have expanded and softened into a diffuse halo, marking the boundary where dark energy's influence becomes paramount over gravity. Paradoxically, Milkomeda will appear more uniform than either predecessor, its shape smoothed by the orbital interactions and gravitational tugs between stars. At the edge of this newly merged galaxy, conditions for star formation will be vastly different from today. With molecular clouds dispersed by billions of years of stellar winds and supernovae explosions, new stars will form in fewer numbers than they do now. The temperature at these outer regions has dropped below -268 degrees Celsius, inhibiting the clumping together of molecules necessary for starbirth. This cooling is a direct result of the universe's expansion, stretching the wavelengths of radiation and reducing the energy available to hold particles together in molecular form. Yet, within this cold expanse, some regions will still harbor pockets of denser gas. These are the nurseries where the last generation of stars before the cosmic nightfall might form, each one a flickering testament to the end of an era. As we look out from the edge of Milkomeda's galactic arm, distant galaxies have retreated beyond visibility due to their light being redshifted out of the visible spectrum. This expansion is not just a static increase in size, but an active reshaping of the galactic structure. The interstellar medium at this distance is so sparse that it resembles the emptiest desert on Earth, yet with no wind to disturb you. Stars are few and far between, their light dimming as they recede into the expanding universe. This environment highlights the profound isolation of galaxies in an increasingly vast cosmos. In 5 billion years, the edge of Milkomeda's galactic arm will have stretched to a radius of approximately 35,000 light-years from its current position. The expansion is not merely passive drifting apart, but an active process that reshapes space itself. As galaxies move further away due to cosmic expansion, they also rotate and evolve internally. This edge marks the point where these two forces, expansion and rotation, are in delicate balance. Here, dark energy's influence becomes dominant, pushing galaxies towards their ultimate fate of isolation. Yet within this vast expanse, there remains a complex dance of gravity, radiation, and matter that will continue to shape the universe for eons to come. The cooling cosmic microwave background radiation at the edge of Milcomeda's galactic arm has dropped to approximately 0.5 Kelvin. This cooling is due to the relentless expansion of the universe, which stretches out the wavelengths of light and other forms of electromagnetic radiation. The cosmic microwave background's temperature drop affects molecular processes within gas clouds, further inhibiting star formation at these outer reaches. Despite this cold environment, some stars persist here, their light stretching towards the expanding horizon, a distant echo of the galaxy's vibrant past. In 5 billion years, the edge of our galactic arm will stretch to a radius of 200,000 light-years from its current position of 100,000 light-years. This expansion is not by growth within, but by an invisible force pushing it apart: dark energy. The edges of this future spiral are moving outward at astonishing speeds, marking the boundary where cosmic expansion overtakes local gravitational forces. Here, stars and gas clouds drift apart, as if pulled by an unseen hand, their movements dictated not just by local gravity, but by the cosmic fabric itself stretching between them. At the edge of our galaxy's arm in 5 billion years, stars will drift apart like scattered grains of sand, carried by dark energy's silent push. The journey through the cosmos ends here tonight. Thank you for being with us on this cosmic voyage. If you enjoyed the ride, please subscribe and leave a like. Good night, traveler, and may the infinite watch over your dreams.